Hello. For those in your room, I'm looking up there because that's where the camera is. Hello, I'm David. I'm the coordinator of the Maths Learning Centre. It's semester 1, 2018. For those of you watching the video in the future, hello from the past. We're doing a revision seminar, and that's enough of my face for right now. Okay. I do that because people would talk to me in the Maths Learning Centre and say, oh, I watched this revision seminar and not realise it was me. So I think I should put my face on them from that point forward. If you watch a really old one, you'll know that I didn't do it then. Only later that I figured that out. Okay, so I am going to just have a quick chat about the Heaviside function. But before I do that, I wouldn't mind if the person who wrote this would like to elaborate this graphs thing. Anything in particular? If you're not brave enough to tell me, that's fine. But do be aware that there are no stupid questions, and I would like you to ask questions during this, because this is for you. This is your revision seminar. I'm not your lecturer. I have no bearing on your course. So, I may never see you again. So you don't need to be embarrassed. Yes? No? Okay. If you think of something as we go along, feel free to ask, okay? And especially if I make a mistake, tell me, because I'm not immune to minus sign errors, just like everybody else. So the Heaviside function, and I may also, while I'm at it, just talk about other piecewise functions as well. But I'll start with this. Okay, well, the Heaviside function is new in Maths 1A this year. It hasn't appeared in my 10 years at Maths Learning Centre until this year. It does appear later on in other courses, and people had to learn it at the time. And so they put it in first year this year so that you're a bit of a step up. No pun intended. Think about that one. So the Heaviside function has this definition. It's 0 sometimes and it's 1 other times. Pretty sure this is true. And it's 0 when x is negative, and it's 1 when x is 0 or positive. So just to read this kind of definition of a function, this is called a piecewise function, the way that this is written. And it's defined in pieces. And one piece is this piece, it's 0, and the other piece is this piece, it's 1, and it tells you where it is. When you're actually deciding the answer to this function, when you're reading it as a human being calculating, you will look at this part first, and then this part will tell you which of these answers that you have to choose. Okay, so just as an example, h of 7, and you'll think, hopefully this has been seen before, but what's going on in your head when you're doing a piecewise function is you go and you have a look at this and you go, all right, 7 is greater than or equal to 0, and so I'll use 1. That's basically the idea. And h of minus 135, and you'll think, let's have a look at this. Minus 135 is less than 0, and so I'll go look that up and I'll use 0. And so that answer is 0. Beautiful. That's pretty much what the Heaviside function is. What makes it hard is when they keep putting stuff inside the Heaviside function and stuff on the outside and multiplying it by things and things like that. And so your Heaviside function is used to make other functions harder. Okay, so just before we get onto it, the graph looks like this. So, same deal when drawing the graph. You'll have a look at your zone and you go x is less than 0. You say, okay, x is less than 0. And in that zone, the formula is 0. And the graph will be y equals 0 in that zone. And so I will draw y equals 0 in that zone. Like that. But on this zone, it's y equals 1. So if you just wrote y equals 1, it would go on forever both ways. But we've got this piece of y equals 1 and this piece of y equals 0, and so that's the Heaviside function. And traditionally, you use open and closed circles to say which dot is part of the graph. So when x is equal to 0, the answer is actually 1, and so that dot is part of the graph, and this dot is not part of the graph. So that's my graph of the Heaviside function. So this is y is equal to h of x. If you're ever on a computer and you want to draw it in something such as, say, Desmos, then you can make a piecewise function in Desmos. But in Desmos, they actually write it in the order that we think it. And so you'll say, when x is less than 0, colon, the answer is 0. And when x is greater than or equal to 0, colon, the answer is 1. And that's the graph. So I've now called that h of x. And I can say, ooh, h of 7 is 1, as it says, and h of minus 135 is 0, as it says. So it can calculate things. Not that we can use Desmos in the exam, but it's a useful thing to be able to do as you're checking your answers now to get a better feel for what things ought to look like. Okay, so document camera. So what I'm going to try and do, this is the point where if I pause at some point and you think I've finished, but you think I have something else that you want to ask me about or a situation I haven't covered, please ask me, okay? I don't want, and I will try and remember to say, is there anything else before I move on? But I may forget, so I'm happy to be interrupted at the appropriate time. So let's have a look at what some things that we could do with the Heaviside function. Let's look at this function. H of x minus 3. So what this tells me is that first I sub in x minus 3, and then I take that number and I figure out what to do with it. And so just as an example, let's see, h of, let's call this f of x. So f of, say, 5 would be h of 5 minus 3, which is h of 2, which is 1, because that's a positive number. Whereas f of 1 would be h of 1 minus 3, which is h of minus 2, which would be 0 because it's a negative number. So what we used to have, if we just did h of 5, it would come out to 1. But if we had done h of 1, it would have come out to 1 as well. So we've changed the place at which it switches over from 0 to 1. And the place it switches over is now 3. Because let's just try some things. F of 2 is h of 2 minus 3, which is h of negative 1, which is 0. F of 2.5 is h of 2.5 minus 3, which is h of negative 0.5, which is still 0. F of 3 is h of 3 minus 3, which is h of 0, which is 1. It switches over to 1 at 3 now. And that's exactly what I would normally expect. If I took any function and I put x minus 3 into it, it will shift the graph of that function over to a different spot. And what it would normally do is shift it forward 3. Because when you're on the inside, it always does the opposite. So, okay, good, it is actually recording. And according to this working here, if I put different numbers in, I have to clear past 3 before the answer is going to be positive on the inside. And so I'm not going to get to 1 until I get to 3. And so the graph will look like this. There's 3. Normally you'd make them equally spaced, sure. But, and it's 0 all the way up to here. And then it's 1 after that. Okay. Beautiful. And let's just check out the computer. There it is, h of x minus 3. even better. Here's h of x minus a. That's h of x minus 0, h of x minus 1, h of x minus 2, h of x minus 3, and so on. If the number is negative, then it would be over the other side. Yay! Okay. I love Desmos. I also like exerting my independence from computers as well, but Desmos is fun when you've got it. So, that is doing that. So let's do another example. What would happen if we did h of x plus 1 plus h of x minus 5? So I reckon we should imagine what would happen with this function by drawing a diagram. You're used to doing sign diagrams and that sort of thing. We're just going to do, in a way, a formula diagram. So I know that if it was just this, then that would switch over from 0 to 1 at -1, because it's always minus whatever is in this position. So that one switches over at -1. And if it was just this, that would switch over at 5. And so over on this side, right. So over on this side, I've got 2 bits. I'm going to draw a diagram here. So this is h of x plus 1, and this is h of x minus 5. So over on this side, h of x plus 1 is 0. And then it switches over to 1 on this side. But this one, x minus 5, doesn't switch over to 1 until here. So we have 3 zones. I feel like I want to color code these. I apologize in advance because I'm going to use pink and green, so if you can't tell the difference between them, I'm sorry. Okay. So, that means I have 3 zones. This zone here where they're both 0, this zone here where one of them is 0 and one of them is 1, and this zone here where they're both 1. And so it looks like when I add them together, I'm going to get 0, 1, and 2. So now I can know what the graph looks like. It's 0 up until this point, and then it's 1, and then it's 2. Lovely. And the only way that I have of writing this function other than using Heavisides would be to use one of those big curly braces. So it's actually 0 when x is less than minus 1. It's 1 when x is from -1 to 2 to 5. I'm looking at the wrong thing there. And it's 2 when x is greater than or equal to 5. So one of the reasons to have the Heaviside function is so that you don't have to use a curly brace like this to write down a function that goes up in steps like this. I could have something that goes up in steps and figure out how to write it in terms of Heaviside functions. So here's a challenge. Here's the graph. And, ooh, gosh, where am I going to put that? Write that in terms of Heaviside functions. or let someone else do it, you know. But it would be better for you if you give it a go. Yeah?
Is it going up to 1?
Yes, let's do that. It is important to know how high it is. So have we got an answer? No, they're not hands raised, they are air graphs. Yes?
hx minus hx minus all the inside.
Is that what you meant?
Yes.
All right, well, let's just check it. So h of x would be 0 here and 1 here. H of x minus 3 would be 0 here and 1 here. So if I draw the same diagram I drew before, this one is 0 here and 1 here and here. And this one is 0 here and here and 1 here. And so the final answer will be 0, 1 and 0, which is exactly what this graph does. So the Heaviside function now can not just tell us things that step up, but they can step up and down if we use additions and subtractions, which is extremely useful for things like electrical signals which turn on and off at certain times. Yes? Ooh, that's fun. So just so that everyone heard that, this is fun. Ooh. Or you're telling me that this is h of x squared minus 3x. Oh, sorry. This is fun. Okay, so this graph, no, I think it's 3x minus x squared. Could be wrong. So x squared minus 3x is a parabola, and it does this. And so we want x squared plus 3x is a parabola that goes that way. And this thing is positive in here and negative out here. So when I do h of a positive number, it comes out to 1. And when I do h of a negative number, it comes out to 0. And so it'll do the thing. That's so exciting. So it's positive. Oh, so positive here and negative here. And so when we do our Heaviside, we're going to get 0 here. That's so cool. I do have an issue with it though. The open and closed circles are at different places. So this one starts at this position and ends at this position. No, it does. It goes on forever, sorry. And it goes like that. And this one, so I'm doing a round when it doesn't go up to that spot. And so when I add these together, the answer of equals 0 actually starts here at 3. And this one goes up to here, like that. Okay, so I have an open circle here, and open circle on the 0 bit, a closed circle on the 1 bit, an open circle on 1 bit, and a closed circle on this one. Whereas this one, there's closed circles there and open circles there, and so it's going to look like this, which has its open and closed circles in different positions. So it's not the same, but it's still cool. That's so exciting. Oh man. Yeah, anyway. that makes me so happy. Oh wow. That's so much fun. You know, yeah, I take a moment. I could finish now. I've learned something today. Okay. That's the sort of creative thinking we want in maths class. And we go, ooh, I could think of if I could think of something that's positive and negative in the correct places, then do Heaviside on it, and it would be plus and 1 and 0 in the correct places. Super cool. Okay, so we've just learned, thank you, that when you put a function inside the Heaviside function, you're essentially creating a new graph which just tells you where the old function is positive and negative. And I guess we could think about it that way with our original ones, couldn't we? This x minus 3 here, if I drew y equals x minus, let me do the original one. This x minus 3 one here, if I drew y is equal to x minus 3, it would cross the x-axis at 3, and it would be negative on one side and positive on the other. And so this switching from 0 to 1 is the same as switching my line from negative to positive. And that's so cool way of thinking about it. I love it. So if you can think of any function that's positive and negative in the correct places, then you'll be good. That's brilliant. Okay. So the other thing that you can do with Heaviside functions is you can turn other functions on and off. F of x is the Heaviside x minus 3 times x squared. Yeah. So, when x is less than 3, so let's just actually figure this one out as a formula. If x is less than 3, then the Heaviside function is 0, and we get 0 times x squared. And if x is greater than or equal to 3, then the Heaviside function is 1, and we get 1 times x squared. So f of x is 0 when x is less than 3, and x squared when x is greater than or equal to 3. And so my Heaviside function is able to turn this function on at x equals 3. So here we go. I've got enough space to fit my graph in. So x squared normally looks like this. But we only want it to start when x is equal to 3. And before that, it's just 0. So my Heaviside function is able to turn this function off before it gets to 3, and then after that it's a parabola. So we should be able to now have any combination of Heaviside things and be able to figure out what happens to them. Mainly the way that you deal with it is to track at all the places where your Heaviside function changes over from 0 to 1, and include all of those in your diagram and figure out what it is at every place in between. And that should do the trick. I'm wondering, because I can't stop doing this, I wonder how I could arrange for this one to be filled and that one to be open with a Heaviside function. I think that will do the trick. Because now, no, that's wrong. No, that's negative in the wrong places. I don't know if I can even do that. So what was that?
If you
Oh, are you saying...
yeah.
Oh, that's so cool. Yes, that'll do it. Yay. So this one is 3 minus x is negative when x is more than 3 and positive when x is less than 3. And so this one is the opposite way around. So this one goes like that. And then we do 1 minus that. Yeah. And that will switch this over. And then we multiply that by x squared. Oh, I've never had so much fun in a revision seminar ever. You know, even including the time when I sang the Pinky Dinky Doo song. I will not do it now for you. I can't do it without a textbook box. But if you watch the Maths 1B revision seminars, eventually when you get there, you may possibly see me sing the orthogonal diagonalization song. Okay. I think I have my feel of the Heaviside function. I feel good about the Heaviside function. You will notice something that we did there in order to really understand what was going on was I kept asking what if questions. So, oh, what if I wanted it this way? What if I wanted to come back down again? What if I had something inside it, thank you very much, other than just an x minus or an x plus? Okay? Those are good questions to ask yourself while you're studying because they help you understand it better, but they also create questions that you've never seen before that you attempt to answer, which is exactly what it's like in an exam. Yeah. Cool. Just a quick question. Have you got the absolute value function in your course? The floor function? No. Oh, it's so sad. I love the floor function. The floor function rounds everything down.
We also have the Dirichlet function.
Oh, the Dirichlet function. Oh, that's fun. So, cool. I might as well just put them in since we've mentioned them. So, the absolute value. So the absolute value is secretly a piecewise function. It has different formulas in different places. When you describe to someone what to do with the absolute value function, then you'll say to them, oh, well, the absolute value of minus 3 is 3, but the absolute value of just 3 is also 3. And you'll say, if it's negative, then you'll remove the minus sign. And if it's not negative, then nothing will happen. And so this function has different actions in different places, which makes it a piecewise function. So it says that if it's negative, we have to do something different to if it was positive or 0. And we know that if it's positive or 0, nothing happens, and so it's just x in this position. And when it's negative, you have to remove the minus sign. And, I mean, you could put in words here, remove the minus sign of x, right? But we'd like a formula. So the only way I can think to remove a minus sign in a formula is to put an extra minus sign in. Because the x is already negative, so if I put minus 3 in that position, I'll have minus 3, which will come out to plus 3. Beautiful. So when you do absolute values of things, you can then use the same sort of reasoning we used in our Heaviside functions to combine absolute values of stuff together to create new functions. So for example, the absolute value of x plus the absolute value of 2x plus 1. And you go, okay, I know that they switch over at the places where there's 0. And so I have a switch when x is 0 and when 2x plus 1 is 0, which means that 2x is minus 1, which means that x is minus a half. And so I will just draw those things spread out enough to be able to make my formula. So let's see. Mod x, or absolute value of x, is minus x over here, it's still minus x here, and it's x here. And the absolute value of 2x plus 1 is, 2x plus 1 is negative over here when x is really big and negative, so it's minus 2x plus 1 here, and it's 2x plus 1 here, and 2x plus 1 here. And so I can now say that f of x, when x is less than minus a half, it's minus x minus 2x plus 1. When x is between negative a half and 0, it's minus x plus 2x plus 1. And when x is more than 0, it's x plus 2x plus 1. And then you can simplify that if you want. Now, I've been very careful not to put equal signs in any of these because I just want to figure out where they should go. So let's just see. This one was like that. So this one here is actually in the top end. And this one here is also in the top end. Okay, good. So see, this one here is part of this. So it's this 0 is part of both of them, so it's this end here that comes out to that. So this would come out to minus 3x minus 1 if x is less than a half, negative a half. X plus 1 from negative a half to x to 0, and 3x plus 1 if x is greater than or equal to 0. Cool. So you'll notice what that is that's 3 separate linear functions that turn on and off at different places. So if I was going to draw it over here in Desmos, I will just draw it and then turn it on. It's a straight line here. That's the 3x minus 1. It's a different straight line here. That's the x plus 1. And it's a different straight line here, and that's the 3x plus 1. And so absolute value functions added together have the tendency to produce something that's made of straight lines, but with kinks. All right. And the Dirichlet function is just crazy. I think I spelt the name right. Is it Dirichlet or just Dirichlet? Who knows? That would be in calculus, wouldn't it? Dirichlet. Got to spell his name right. So the Dirichlet function is insane. It is that 1 if x is rational, and 0 if x is not rational. Have you seen that symbol before for the rational numbers?
Yep.
All right, now you have, if you haven't. The Q stands for quotient, which is how you create a fraction by doing a quotient. We can't use R because we already used R for real. So, yeah. And that's insane. Like, it's impossible to draw. Because no matter how finely grained you make, no matter how far you zoom in, there is always a rational number and an irrational number in that zone. So no matter how close in you zoom, you'll always get something that gives you a 1 and something that gives you a 0. And so when you draw it, it just looks like this. Now it looks like it's not a function because it has 2 answers, but that's an illusion because if you pick an actual number, it will just be on one of these 2 lines. But because the numbers are so densely packed, you can't see which is which from this distance, or from any distance. That is the magic of the rational numbers in the real numbers. You can get as close as you want to any number using a fraction. You just might not be able to get there. So there you go. It's awful. And if you multiply the Dirichlet function by an ordinary function like x squared, then you'll get x squared when it's rational and 0 when it's not. And it will look like a parabola and the x-axis, but it's not really. It's just most of the parabola and most of the x-axis. So actually, technically, it looks like it's not much, but it looks like it's a lot, but technically there are way more real numbers than rational numbers. And so it's actually not much of the parabola and most of the x-axis. Yes?
We're not going to be asked to get the derivative of Dirichlet.
Oh, you can't differentiate the Dirichlet function.
That's
So if your lecturer said, what's the derivative of the Dirichlet function, you would say it doesn't exist. Dirichlet function is not differentiable. You can't differentiate it. So interestingly, the Dirichlet function times x squared, you can't differentiate it anywhere except when x is 0, then you can differentiate it there, and the derivative is 0. This function was invented specifically to make crazy things happen. Okay, they call it a pathological function. Like that's what they call them. There's a whole book of them called Counterexamples in Analysis. Yeah, but you may be asked to differentiate a combination of absolute values. So if you want to differentiate combination of absolute values, the only way to do it is to figure out what its true formula is as a piecewise function, and then differentiate each of those separately. But you should know that when you differentiate, well, I'm going to write this down actually because it's no point saying it without writing it. When you differentiate an absolute value function, it has those kinks at the corners there, kinks at the crossover points. You can't differentiate a function if it has a sharp kink like that. So when you do the derivative of a piecewise function, it has the tendency, so if I did f of x equals from before, find f dashed x. So the true formula for this is minus 3x minus 1 plus 1 and 3x plus 1 when x is greater than or equal to 0. Sorry. You can tell that I only use a document camera like once a semester. By the end of the revision seminars, I'm really good at it, but yours is only the third one. So if you want to differentiate this, you'll differentiate each piece separately. So the derivative of that is minus 3. And the derivative of that is 1. And the derivative of this is 3. And you'll have to say that f dashed x does not exist at x is equal to minus a half or 0. Because those places, the slope coming from this side is trying to be minus 3, and the slope coming from the other side is trying to be 1, and it can't be both at the same time. And so it just doesn't exist. I don't know if that's part of Maths 1A, but at least you know now. Yeah. So in very rare circumstances, they do line up. So if you happen to get one where both the slopes were 1, then the derivative would exist at that spot because they line up correctly. All right. So, how are people feeling about our piecewise functions? All right, we've got at least 2 thumbs up, so I'm going to move forward. Okay. So I need to choose something else to talk about. Related limits, maybe? Maybe related rates. All right. I might do some limits. If you have anything in particular that you were thinking about with limits, please do try and get them clear in your head, the questions you want to ask. Okay. The reason I wanted to do this is the revision seminar that I currently have on limits is for Maths 1B, the old Maths 1B, and it does both ordinary limits and multivariable limits, and that's just a bit intimidating when it's not in this course. So, yeah. So, limits. The reason they talk about limits in this course is probably to define the derivative, which seems like a lot of effort for really not much gain. But mathematicians are nothing if not precise. And when Newton created and Leibniz created calculus back in the day, like in the 1700s, they didn't do any of this stuff because they were physicists. And then mathematicians had to come in later after several hundred years and fix up the details. And so now when we teach maths, we teach you the details because we think that's important. So, as I've said to many people, Mathematics 1A is also Mathematicians 1A. You get to learn how mathematicians think and behave. And one of the things they love is definitions. And so that's why we have limits before derivatives. Even though it's perfectly possible to calculate derivatives without knowing anything about limits, but that's not how mathematicians think. They need definitions first. So, we are going to talk about limits and continuity, I imagine. So the idea of a limit is that in a lot of situations with a function, I don't actually care what happens at a specific spot, I just care what happens nearby. The real numbers have this wonderful property of being able to get as close as you want to something without actually getting there. The natural numbers don't do that. You know, you keep counting downwards and you'll just get to 0 eventually, and you can't get any closer to 0 than 1 without being 0. But in the real numbers, you can get as close as you want to anything and not actually get there. So here's an idea. So I can imagine going, 1 and 1.9 and 1.99 and 1.999 and 1.9999 and so on. And I know that I'm getting closer to 2, but I can do this sequence as long as I want, and I will never be at 2. Unless I do it forever. Okay? So this is none of these are equal to 2. But I can get as close as I want. That's the idea of limits. I don't really care that it gets to 2. I care I can get as close to 2 as I want. And so I imagine that if I did this process forever, it would get to 2. That's the concept of limits. And so you've been doing limits since you first did repeating decimals. Back in year 6, maybe? My daughter's in year 4 and she hasn't seen them, so I'm pretty sure that it's sometime after that. So since you first did repeating decimals, that's when you first did limits. Okay, so I can get there as close as I want, and so I would say something like the limit, as I don't even know how to write this, the limit of this sequence is 2. Okay? And so I have this thing that I want to be equal to 2. It looks like it's going to be equal to 2. I can get as close as I want. And so I have to have and I want to make a statement with an equal sign in it because that makes me feel good about what I've written. And so I want to say equals 2. And so I need a thing on this side that can be equal to 2. None of the elements of the sequence are equal to 2. So I create this new object which I call the limit of the sequence. Great. And when I do limits with functions, I try and coordinate this with the input and the output of the function at the same time. So I can imagine that this might be a function of, say, where I'm up to, 1, 2, 3, 4, 5. And I can say that as x goes to infinity, the actual answer goes to 2. There you go. I'm making this up as I go along, by the way, so just be aware of that. Okay, so that's the idea of limits. And so what we have is we have a function, we have a location, and we want to know what does f of x, this is f of x, my location is A, what does it get closest to as x gets close to A? And that thing is called the limit. The limit as x approaches A of f of x. That is the answer to that question. And the reason I care about this is that for some functions that you've already seen, that answer is different depending on which direction you come. So when we did the Heaviside function, okay, just a second. So at the moment this is saying being close to A, and I can be close to A on one side or the other. I'm just going to check something in your notes. I'm just checking to see if you've done one-sided limits or not. It'd be nice if I could have a written example that included the thing I wanted. Oh, come on. Oh, for the sake of Frel. Okay. So, I may have to introduce a notation that's not in your course, I'm sorry, to finish my sentence. It is possible to approach the limit from either side. If you see this notation in looking on online resources, this is what it means. I could say, I could come at A from above, like from the right, and then it would be the limit as x goes to A from the positive side. And I could come at A from below, which would mean that limit as x goes to A from the negative side of f of x. I don't know if that's in your course, but if you see it in online resources, that's what it means. And the reason I mention that is that the Heaviside function, which looks like that, the limit as x approaches 0 from the positive side of the Heaviside function is 1. Because as I come in on this side, it goes to 1. But the limit as x approaches 0 from the negative side of the Heaviside function is 0. Because if I come in this side, it goes to 0. That's what it's going towards. And that's the idea of a limit. My function might be going towards a particular number, and I don't really care what happens as it gets there because I'm trying to describe where it's going. The moment it gets to 0, it jumps up to 1. But I can get as close to this spot as I need. So that's the idea of limits, is trying to talk about what the function is doing as you get close, even if it does something slightly different when you actually get there. That's the idea of limits. And the reason that's so important for derivatives is that derivatives are about slopes at a single point, which doesn't actually make sense at all. Function slope is between 2 points. Like the definition of slope is between 2 points. So it makes not the slightest sense to talk about the slope at a single point. But what we do is we make it make sense by saying, well, we can make the little line that we want as small as we need. And so since it seems to be going towards this number, that's what we say the slope is. And that's what limits are about. We seem to be going towards this place, and so that's the place they're going. Right. So the key to limits is being able to successfully manage the limit laws. As far as I'm aware, you do not need to know which number limit law is which number. You just need to be able to use them. And I know that back when you did them in the assignment, they said, oh, you reference the limit law. You don't usually have to do that in the exam because they're comfortable with you being able to do it. So you don't have to know which number it is. You could, if you wanted to, say the limit law for multiplication or the limit law for division or whatever. So let's have a think about that. So the limit laws say that if I add functions together, then if one function is going to 2 and the other function is going to 3, then the sum will go to 5. It just says that I can expand limits out. I can do the limits separately and just add them together afterwards. Beautiful. And if I multiply it by something, that's totally going to be the same thing, right? So, if my function is going towards 3, then if I want the limit of 5 times my function, then it'll go towards 15. I think in your book these are combined into one rule, but I find them easier to think about separately. I should say that all of this only applies if your function's limits actually exist in the first place. If they don't exist, then all bets are off and you can just, if the limits exist. Okay. And the next limit law is that if both limits exist and you multiply stuff together, then you can just do the limits separately. Which is great. And then there's a limit law for division. Now this is really cool. So this one says that, look, as long as both of these limits exist then I can multiply them together. But if one of them doesn't exist, it is technically possible sometimes for the multiplication limit to still exist anyway, even if neither of the other ones do. So this doesn't tell you whether a limit exists or not. It just helps you to calculate when you know it does. But the division limit law tells you when a limit exists. So this is not the formal way of writing it. All right. So this will definitely not exist. And that could mean it's infinity, it could mean it's minus infinity, it could mean nothing at all. Okay? It will definitely not exist if the limit of the bottom is 0. And the limit of the top isn't 0. In fact, I'm not even going to say this. I'm just going to put some inverted commas and say not 0 divided by 0. It has to be in quote marks because it's not really that, because I don't really care what happens when I'm at that spot. And it will be 0 right? And it will be whatever the answer is if the bottom isn't 0. Okay, so it'll be, the limit of f over the limit of g, as long as it's anything over not 0. And it will be who knows what the hell is going on if it's 0 over 0. Right. So what this bit here usually means is that there is more work to do. More work. That's the limit law for division. This is the only limit law that tells you whether a limit exists or not. So if the limit of the bottom is 0 and the limit of the top isn't 0, limit does not exist. If the limit of the bottom and the limit of the top are both 0, you can't tell and you have more work to do in order to decide. And if the limit of the bottom isn't 0, well, go for it. It's whatever the answer is. That means that in tricky situations where it's hard to tell what the limit is, the easiest way to tell is to write it as a fraction. And there's one more limit law, which I'm really hoping is in your book, which is why I needed your notes. Yep. There is one more limit law, which tells you what happens when you put limits inside other limits. So it has two versions. So one version is this. If, and it's very important to talk about this, if the limit of x goes to a of g of x is whatever it is, b, and the limit as g goes to b of f of g exists, then the limit as x goes to a of f of g of x is the limit, is f of the limit as x goes to a of g of x. So that's one version of it. You're never asked to actually write down the formal statements of the limit laws, but the point is that you can bring limits inside functions as long as the limit exists at the place where the inside function is going. All right. I will give an example of that momentarily. And there is another version of this. This only works in situations where f is actually defined at whatever this limit is. But there are some functions that still have a limit anyway, even though they're undefined at that spot. And so you can do this version, and I call it limits by substitution. And so you go to find the limit as x approaches a of f of g of x, then you go let u equals g of x, then as x approaches a, that means that u approaches b, and therefore the limit as x approaches a of f of g of x is the limit as u approaches b of f of u. I will give an example of this, but this is the same thing as what I did before, but what they feel different. This one here, I just brought the limit inside the function. Whereas this one here, I replaced this with something else and made a new limit. All right. Rather than make up examples at this time, does anyone have any examples of limit calculations that they found difficult that they would like me to talk about? Or ones that they didn't find difficult that I'd like me to talk about? See, that gives you an out, right? Nobody will know whether you thought it was difficult or not. Otherwise, I'll attempt to make them up, but, you know, I often get ones that are impossible if I try and make them up. All right, I do have one. I just want to check something. Did you do... I don't think you spend all that much time calculating limits in this course. I can't find any examples, which is just annoying. Man, that's annoying. All right. And page 26? Oh, yeah. Okay. So I'm going to do one. Okay, this is a classic. The limit as x approaches 3 of x squared minus 9 over x minus 3. It's already written as a fraction. So I need to decide whether the limit exists or not. And also, if it does exist, need to figure out what it is. So if x, let's just see what happens when x is 3. If I do get all the way to 3, then the top is 3 squared, which is 9, minus 9, which is 0. And the bottom is 0. So my limit laws tell me nothing. I have to do something to turn this into a limit that isn't 0 over 0 anymore so that I can tell what to do. That's my big decision-making process. Make it not 0 over 0. So the nice thing about polynomials is that if a polynomial is 0 at 3, then x minus 3 must go into it. And so it must be possible to divide x squared minus 9 by x minus 3 to figure out what it is. So it should be possible to factorize the top. And that's how to factorize x squared minus 9. So the fact that they both came out to 0 told me that it should be possible to factorize the top and the bottom so that there was an x minus 3. And here's the really sneaky bit of limits. I don't care what happens when x is actually equal to 3. I only care what happens when I'm close to 3. And no matter how close to 3 I am without being equal to 3, x minus 3 isn't 0. And so therefore I can divide the top and the bottom of this fraction by x minus 3. I can do x minus 3 divided by x minus 3 because it's not 0. Because I'm not exactly at the point where x is 3. So I can do this. And this limit is a brand new limit, and I can ignore everything else I've seen so far, and I can go, well, when x is 3, this is 6. Ta-da! That's the major use of that rule. I didn't even really use any of the limit laws there. I used the fact that one of the limit laws tells me that I need to do more work. The fact that it's 0 over 0. Give me a second. This is stupid, this one, but I want to make a point. Here we go. So it's the same as the one above. Well, how is it different to the one above? Sorry? Oh, just a second. So how is it different? Just a second, I should do it on the screen. What are you saying? X squared minus 13 there. So this instead of an x has an x squared minus 13. And this instead of an x has an x squared minus 13 as well. Ooh, interesting. Okay, so nothing up my sleeves. When x goes to 4, x squared minus 13 goes to what? I heard several answers. What? Yell. When x goes to 4, what does x squared minus 13 become? 3. Ooh, interesting. So watch this. Let u equals x squared minus 13. Then x going to 4 means that u goes to 3. And so therefore, the limit as x goes to 4 of x squared minus 13 squared minus 9 over x squared minus 13 minus 3 is the same as the limit as u goes to 3 of u squared minus 9 over u minus 3, which was 6 because we just figured that out. Okay. It doesn't matter what letter this is, right? So it doesn't matter what letter this is. I could replace them all with x's and it would be the same. The point I want to make is that if you notice a piece of it repeats, you can do substitution the same as you do with integration. And you can do your limit that way. The reason I can't use the limit law by just bringing the limit as x goes to 4 inside those brackets is because the function doesn't exist. Like 3 squared minus 9 over 3 minus 3 is 0 over 0, which doesn't exist. It's not a thing. So this is the best way of doing it. So that's me using the limit by substitution law. There you go. I don't know if it's necessary, but it's fun. Where by fun I mean marginally more fun than not doing it. Okay. Cool. So, I mean, the classic limits that you want to know are really the ones involving fractions like that. And the reason we care so much is because of derivatives, because a derivative is defined as a limit. F dash x is defined to be a limit That's the definition of the derivative, and it's a limit. So actually when we do a derivative, we are calculating a limit at every point on the curve. A separate limit for each one. And they all come out to their own answers. And this limit's actually quite problematic because when h is 0, the top is 0 because it's just f of x minus f of x. And the bottom is 0. So when h goes to 0, we get a 0 over 0 situation, which my limit laws don't tell me whether it exists or not. So derivative limits tend to be that situation, the 0 over 0 situation. They are guaranteed to be that situation. And if you want to do them by first principles, then you have to convert your limit into something that's not 0 over 0 anymore. Guaranteed to be 0 over 0 when you do a limit by derivatives. Whoops, sorry. It's guaranteed to be 0 over 0 when you do a limit by derivatives, which means you're going to have to do the sort of thing I did before, where you cancel stuff out so that it's not 0 over 0 anymore. And the moment it's not 0 over 0, that's when you can calculate what it is. Right. Ask me some questions. Could be about this, yeah?
Can you run through subspaces and bases and all that?
Oh, yeah, I suppose. Okay. All right. Now, for those who didn't hear, it was, can you run through subspaces and basis and all of that? There is no clock in here. 40 minutes. It'll be a run through. Every year I talk about subspaces and basis because it's one of the hardest bits in Maths 1A conceptually. And every year I sigh because it's never as good as the one I did back in 2014, which is on the website if you want to have a look at it. Okay? And I just every year just end up getting more and more of them on the list and say, like, you know what, if you haven't got enough from the first one, try another one and maybe I'll have said something different that time. So maybe I will talk about that because there were several there on the page. There is a related rates one on there from a different course, so hopefully that'll be enough. Right. All right. Okay. Subspace is actually my favourite bit of Maths 1A as a mathematician because they're just cool. Everything's all connected. And if I think they're going to change the Maths 1A B curriculum the way I think they're going to, you'll still have subspaces in Maths 1B. And so you'll just jump off from where we left off. So I'm just going to have a quick inverses, convex sets, slack variables. Determinants, elementary operations. Where are the subspaces? Oh, really? Okay. Oh, yes, right. It's just called spanning sets and linearly independent sets as opposed to subspaces. But we all know what it's really about. Okay, cool. Got it. Right. It's important to be able to think about subspaces in relation to matrices as well, which came after in this course, but I'm going to sort of mix them together here, possibly. So, a bit of philosophy. To a mathematician, a vector is a thing that you can do scalar multiplication and addition to. I do scalar multiplication and plus. That's what a mathematician thinks a vector is. Okay? And most of the time, okay, so to a physicist, a vector is a quantity that has both magnitude and direction, famously in Despicable Me. But to a mathematician, that's not relevant. It's just the fact that I'm capable of adding them in a reasonable sort of way and multiplying them by scalars. That is what makes them vectors. And most of the time, to a mathematician, a vector is just a list of coordinates. Now, if you ever go further in the abstract mathematics here, you will stop thinking of vectors as lists of coordinates and just think of them this way, and anything that satisfies this can be thought of as a vector. So when you do differential equations in either differential equations 2 or engineering maths 2A, you start to think of functions as vectors. And that's fun too. So this is like, you know, the big idea. And the slightly smaller idea is in Maths 1A, a vector is just a list of coordinates. Okay? And the reason I think it's a vector is because if I take two lists of coordinates with the same number of coordinates, I can add them and I can multiply them by scalars. That's great. And if I collect them all together, they call it a vector space. So the second thing about the way Maths 1A vectors work is that to a physicist, a vector is an arrow. But in physics, a force vector doesn't live on the page where you draw it. When you draw a diagram in physics, and you draw a diagram of your little box with the gravity and the whatever, and you put a force arrow on it, that arrow is not actually living in the same place where the box is. it lives wherever forces live. I don't know where they live, but it's not part of the drawing. And when they add and subtract, they go over to put head to tail and they do their thing. So it's very important to realise that vectors aren't really arrows. They're just sizes of things that get added together. So in Maths 1A, if you're trying to add it and multiply it by scalars at the moment, then it's an arrow. If it's just sitting all by itself, then it's a dot. So coordinates can either be journeys or positions. Okay, and they're only journeys when you're adding them. Otherwise, they're just positions. So maybe this is 1, 1, and this is 1 minus a half, and this is 0.81. They are journeys, but you might have the position 1, 5, and it would be here. So just remember that if a vector is sitting alone all by itself and it's not currently being added to anything, you're thinking of it as a dot. Okay. And even if you're doing your adding, the final answer is still just a dot. It's not an arrow from the origin to that spot, it's just a dot. Okay. The reason I need to say that is because when I'm talking about a subspace, I'm thinking of a collection of dots. So I might be able to create any sets of points that I want by having a rule to tell me whether it's in the set or not. And you realise I'm not up to subspaces yet, but I need to say these things so that the things I have to say about subspaces make sense. If you're in or out. Okay. So just some examples of sets of points. You might be seeing the set of points x, y, z such that x plus y minus 3z is 0. That's a set, and this is the rule here. The rule is that if you're in this set, you satisfy this equation, and if you're not in this set, you don't satisfy this equation. So I can tell that the vector 1, 0, 0 is not in this set, because when I sub it into here, it doesn't come out to 0 like it should. Some vectors have their rule in a different position. Not vectors, sets of vectors. So this is the rule for telling if you're in or out. In this situation, it's this that tells if you're in or out. Okay, so if you're thinking about things that are this shape, so I can make these points as much as I want. This says that the set contains things with coordinates a and a squared plus 1 as long as a is in R. And so I could pick a to be 1 and I'd get the point 1, 2. I could pick a to be 3 and I'd get 3, 10. And I can make these vectors as long as to as many of them as I want. But if I randomly picked a vector like 5, 17, I would have to do a bit of a check to see if it's that shape to tell if it's in the vector in the set or not. Okay, so this is sets. And what we're really interested in is an extremely special kind of set when we're making a subspace. There are two other main ways of making sets. One is just to have a list of all the things that are in the set. And the rule of being in a set is it in the list or not? So you could also just have 1, 0, 1, 5, 0, minus 3, 5, 5, 5. And the rule is just, is it in the list? So they're the three main ways of making a set. And every one of them has a rule for telling whether you're in the set or not. And that's actually the definition of a set. A set in mathematics is a thing that has stuff in it that has a rule for telling whether stuff is in or out. And there are some things that don't have rules for telling whether you're in or out that make sense, and so they don't count as sets. such as the set of words that describe themselves is not a set. Because the word non-self-describing well, if it is non-self-describing, then it's self-describing. Damn it! And so you can't create a collection of words that describe themselves because there are some words that you can't tell whether they're in or not. So maths is usually a little easier than that, at least with subspaces. So you just don't want to make them refer to themselves. You just don't want a circular reference. Okay, that's a whole. You can tell I'm getting tired. Started to ramble about random crap. We need to tell a very special kind of set. Okay, so the first thing to note is that a subspace is a set. So since it is a set, every subspace has at least one rule to tell you whether you're in the subspace or not in the subspace. Okay, so it's a special kind of set, which means it's a collection of dots, and I could colour in all the dots and make, a drawing. And there's a rule for telling whether I'm in the set or not. And it's a very special kind of set because it's inescapable using the things that vectors do. So vectors are vectors because you add them and you scale and multiply them. A subspace is a subspace because you can't get out of it by doing those operations. So that's not the formal definition. Okay, a subspace is a subspace because you can't get out of it by doing vector operations. So this prefix sub is actually a common one in mathematics. The real numbers are called a field, and the rational numbers are a subfield because you can't get out of the rational numbers by doing times, minus, plus, or divide. If you start with fractions and you do times, minus, plus, divide, you've still got more fractions, so you can't get out of the rational numbers by doing the things that numbers do, and so therefore it's a subfield of numbers. So we're going to do that with vectors too. We can't get out of subspaces by doing the thing that vectors do, which is addition and subtraction, addition and scale and multiplication. And so we're going to go, the definition is a subspace. W is a subspace when. So you can't get out of it by doing the things that vectors do. So if you and I'm going to leave a gap because I want to talk about something in a second. If U is in W, then K times U is in W as well, no matter what K is. And if U and V are in W, then U plus V is in W, no matter what U and V are. But there is one other rule that I found that is extremely important to know about vectors, is that you can't have vectors unless there's a zero. Okay, so you can't be a subspace unless there's something in it at all. Like I could say, I can think of a set. I think of all of the vectors whose first coordinate squared is -1. You go, David, there aren't any of those. Aha, yes, okay. And so my set is empty, it doesn't have anything in it. And that's stupid. You can't have a subspace with nothing in it at all. And so you need there to be something in your subspace. Right. Also, you can't really do addition properly unless there's a zero. Because otherwise, if you add something to its negative, then what's going to happen? So you need there to be a zero if it really is a subspace, it has to have zero in it, because vectors just need a zero to be there. But really that's just there because you need at least one vector in it. And you might as well check the zero vector. it is technically possible to actually do this and just say, there is a vector in it, here it is, and it doesn't have to be the 0 vector, and then check those rules and it'll be fine, because if the scalar multiplication rule worked, then the 0 is in there anyway. But you have to have a vector in there first. So in Maths 1A, they say that this is the actual law here, and not just checking a random vector. But if you look at subspaces elsewhere in the world, so if you look online at YouTube videos from other places in the world, their first rule may be it's not empty. So just wanted to point that out to you. So that's our definition. But the problem with mathematicians is they believe, mainly through careful conditioning over the course of their degree, they believe that definitions are enough to understand things. And this is not actually true. Human beings do not understand things by definition. Human beings understand things by examples. Now, not that mathematicians aren't human beings, they've just we, as mathematicians, have just, most of us, forgotten that that's how we understand things. When a mathematician is faced with a definition, the first thing they will do is make a list of things that satisfy the definition and a list of things that don't. So the first response of a mathematician to seeing a definition is to make a list of examples. The definition just helps us when we're not sure. It's the same in science, okay? You can look at a dog and know it's a dog in biology, but there are some animals that you can look at and go, not sure, and so you look up the list of things that definitely means it's a dog, and then you'll be able to tell or not, okay? You know, is it a wild dog or is it a wild fox? I don't know. And so you'll try and figure it out. So that's what we're going to do with subspaces. We are just going to have a list of things that are subspaces and a list of things that aren't. But because we're mathematicians, we're going to have a proof that they really are subspaces or a proof that they really aren't. So this is the most important thing about subspaces that I could pass on to you that helped me understand it and helps me help other people understand it. And it's this list of examples of things that are and things that aren't. And there are two of them that you have seen. And I'm just going to have a look at it. This is your notes. And there's the definition of subspace. And the first thing that happened after that definition was two pages of examples. That says to you that it's the examples that help you understand the definition. Because without them, the definition doesn't mean anything. So, there are two main types of ways to make subspaces. And the two ways of making subspaces are to span things. Just a second. Okay, here's my ways to make subspaces. Span anything. If you create the span of any vectors, it is automatically a subspace. And vectors and linear equations equal to 0. These are the two main ways to make subspaces. If you see something that is the span of anything at all, it is guaranteed to be a subspace. Because the span is literally created by taking some small number of options and doing all the possible adding and multiplying by scalars that you can possibly do. And so therefore you can't escape because you did all the options. And the linear equations thing, well, that's a bit more mystical. But if you have some vectors and the rule for telling whether they're in or out is that they solve linear equations that are equal to 0, then they also must be a subspace every time. Which allows you to decide just by looking at how it's written whether it's a subspace or not. Okay. So just some advice here. If you're... Oh, my pencils are dead. If your span that you think is a span misses out on any one of the linear combinations, then it's not a subspace. So just note. If any one linear combination is missing, then it can't be a subspace. I mean, you might miss most of them, but if you miss even one, then it's not a subspace. And over here, if it's not a linear equation, so it's got a squared in it, or maybe some of the variables are multiplied by each other, then it's usually not a subspace. And you've noticed very carefully that I've said usually, because sometimes there's a double bluff and it turns out to be a subspace after all. But I will show you the situations that normally happens in. So here we go, examples. The span of 1, 3, 5 and 2, 6, 10 is a subspace because it's a span. Nothing else to it, definitely subspace. If you were asked to prove it was a subspace, then you would definitely have to go back and check all three of the rules. But if you're just asked, is this a subspace, yes or no, you can just say yes, because it's a span. If that's all you have to do, then you can just make your decision. I want to point something out. These vectors are not linearly independent, and it doesn't matter. A span of anything is always a subspace. The linearly independent is about basis, which is a separate idea. Related, but separate. Okay, so so I have the set of A, B, A minus 3B, such that A and B are in R. Your lecturer might write this with a colon instead of a vertical line, like two dots. People get to choose what they do with that, so please don't be distressed if I use the vertical line. I just find if I draw two dots, I can't see them afterwards, so yeah. Well, this is A lots of 1, 0, 1, and B lots of 0, 1, minus 3. So what I've done is I've gone through and said, well, there's an A here, and there's one of them. There's no A's here, there's one A here. And then I've said, well, there's no B's here, and there's one B here, and there's minus 3 B's here. So if I expand that all out, if I actually multiply that all out and add them together, it will come out to be equal to that. And this is exactly what span is. Span is all the linear combinations of something. So this is totally the span of 1, 0, 1 and 0, 1, minus 3, which is a subspace because it's a span. All spans are subspaces. So this is one way of showing that something's a subspace without technically proving it, is to rewrite it, what you've got, as a span. So let's do some what ifs. If this had an A squared, then I'd be stuffed, because I wouldn't be able to do this trick. I could only remove one of the A's and there'd still be an A left behind. It wouldn't be a linear combination of a known vector, and so it wouldn't be a subspace. So I'm just going to pop that in. So I'm looking at this and I'm thinking, if that A squared is bothering me, subspaces tend to be linear in all respects, and so I feel like that's not a subspace. But just because I can't separate it into its two different pieces doesn't mean that it's not possible, and so I need to be sure, and so I'm going to suspect that it's not a subspace. And I'm going to show that it really isn't a subspace by breaking one of the rules. So let's see. Well, the zero vector's in there, so that's all good. So the next one on my list is scalar multiplication. And the reason I put scalar multiplication first before addition is because it only requires one vector to break, whereas addition requires two vectors to break. And so it's usually easier to do. So let's see, I need to think of a vector that's in here. And I reckon it needs to include something with the a, where the a squared and the a are different. Because if the a squared and the a are the same, then I could totally do this. So let's maybe pick a equals 2 and go a equals 2, b equals, well, why not let's do 0 and see what happens. 4, 0, 2. Okay. And if I multiply that by something, it's supposed to not be in there anymore. So that's in my, let's give it a name. That's in W. Cool, because I made it that way. So now let's try, there's too many 2's, so I'm going to go 3. 3 times 4, 0, 2 is 12, 0, 6. Okay. So let's see, this would give me a b equals 0, which would mean therefore that the a would have to be 6. And so the first coordinate should be 6 squared, which it isn't. Because it's 12, which is not 12. So therefore 3 times 4, 0, 2 is not in W. So I had a vector that was in W, I multiplied it by something and it wasn't in W anymore, and now, therefore, it's not a subspace because I broke one of the rules. But one of the important points I want to make here is the only reason I thought to do that was because I looked at it and went, if it was a span, it would be a subspace, and I can't separate that out into a linear combination. Yes?
Is this the closure under scalar multiplication?
This is closure under scalar multiplication. Only this one's not closed. So that's the correct term for it. This rule just here is called closed under scalar multiplication. That rule just there. And I was very careful to use the can't get out, because it's closed. That's why it's called closed, because you can't get out. The door is closed. Okay. Cool, that's span. Okay, and I do want to make one more. That set so someone tell me how this is similar and how this is different to the other example that I've got. Sorry? That Z is the integers. But yes, you have pointed out that these two are different. So this was a span before, and this is still being able to separate it into linear combinations, but I'm not using all the linear combinations. I'm only using some of them. In particular, I'm not using the ones where I can use a equals a half, for example. So because I'm not using all the linear combinations, it's not a subspace. Not all linear combinations. Therefore, not a subspace. Of course, that's what I'm thinking in my head. Right, this is what I'm thinking. But what I write on my page is something like 1, 1, minus 2 is in W, but a half, minus 1 is not in W. And I know it's not in W because the first coordinate is supposed to be an integer if it's in W, and it's not anymore. So not closed in a scalar multiplication, therefore not a subspace. But what I was thinking was, oh, well, you know, if it had all of these, if it was supposed to be everything in R, then it would be a subspace, but I'm only using some of the combinations, so it's not a subspace. Some of the combinations are missing, so it's not a subspace. Okay. So the other kind is linear equations. X plus y equals 0, z is equal to 0. That's definitely a subspace. Guaranteed to be a subspace because these are both linear equations equal to 0. In fact, the formal word for that is homogeneous linear equations, therefore subspace. It doesn't matter how many variables are involved in those equations. You might not use all three of the x and the y and the z. It doesn't matter how many equations there are. It doesn't matter if you repeat some of the equations. As long as they're all equal to 0 and they're all linear, then it's a subspace. Yeah. Let's switch to pen. Okay, so I've made one change to this, other than writing in pen. I've made one change, and it's this. This isn't a linear equation. So because it's not a linear equation, I suspect it's not a subspace. So I suspect that's not a subspace because it's not a linear equation. So I'll run through my rules. Zero vector is fine, that satisfies both equations. Scalar multiplication, I'd have to think of something that was in it. So I wouldn't pick 1 or 0 for x because those two numbers don't change when you square them, and so I should pick something that's different when I square it. Maybe minus 1. Yeah, let's do that. Yep, that's in W. Since minus 1 squared minus 1 plus negative 1 is 0, and 0 is 0, so it satisfies the equations. But now if I multiply by negative 1, then that will not make any difference to the squared, but it will make a difference to the y. Since 1 squared plus 1 is 2, which isn't 0. So x squared plus y is now 2, and it's not 0 anymore. And so, therefore, not a subspace. So the reason I chose minus 1 is because of the squared, and minus the negative numbers are usually what makes the squares go funny. All right, I have one more change to make. I'm going to do another example that's just a little bit different to this one. I fit it all on the screen at once? Just. Okay? So now, they're both squared. X squared and y squared are both squared. So that trick I did with the minuses isn't going to help. Actually, just a second. If x was -1, then x squared plus y squared could never be 0. In fact, the only way to get x squared and y squared, x squared plus y squared to be 0 is for x and y to both be 0. So this is in fact the same as x, y, z, such that x is 0 and y is 0 and z is 0. They're linear equations that are equal to 0, hence it's a subspace. Double bluff. I mean, if you're really looking closely, this is just the point 0, 0, 0. That's the only point in this set. And 0, 0, 0, just the 0 vector is just by itself is a subspace, because you can't escape it by doing additional scalar multiplication. And it's got the 0 vector in it, because it is the 0 vector. Okay, that's deciding if things are subspaces, and we're already at 3 o'clock, so I'm supposed to finish soon. I do have several examples of proving that things are subspaces. I do still have half an hour on my clock, so I could do a couple of them. If you're willing to stay. I will not be offended at all if you just run away. Okay, so feel free to go if you want to, but I might do a couple of proofs. Okay. Before I do the proofs, I do want to say one more thing about subspaces. If you do leave, could you do it quietly, because I'm still talking. That's not about subspaces, that's just something else. So, you know how I said that subspaces can be written in 2 ways? One is as a span, and the other one is as the solution to linear equations. The whole point of a basis is to do this. So I can make subspaces in multiple different ways. But it turns out that no matter how I've made my subspace, I can rewrite it as the span of something. Every subspace is the span of something. And that's what a basis is for. A basis is for rewriting your subspace as the span of something. Now, it will be a subspace if it's a span of anything, but if you make sure that that thing is linearly independent, then you'll be able to make your subspace in the simplest possible way. I just wanted to say that before I moved on. Okay. So I have, there's no screen there. I have a particular way I go about doing proofs. And someone did say advice for proofs, right? In linear algebra. All proofs in mathematics hang upon the definitions. So if you're asked to prove something, you must use the definition somewhere. That's the first thing you need to know about proofs. And so if you're going to do a proof, you need to know the definition so that you can tell when you've used it. Sometimes you don't have to use the definition and you can use some other theorem that they've told you, but almost always a proof uses a definition. And if you want to prove that something's a subspace, you must use the definition of subspace. Now, the definition of subspace actually has 3 different parts, and so proving that something's a subspace is actually 3 separate proofs, just glued together. So, we have to use those, we have to create a proof based on those 3 separate definitions. And a useful thing about the way definitions work, and the way the things you want to prove work, is it's a grammar problem more than anything else. If your statement that you have is an if-then statement, then your proof will normally be structured as a suppose therefore. So if you're trying to prove an if then your proof will normally look like suppose therefore. Okay? And that's more of a grammar problem than anything else. And if your proof says there exists then somewhere in your, if your thing you're trying to prove says there exists, then somewhere in your proof you're likely to say, consider this thing. You won't say it that way, of course. So if you want to say, well, there exists an x such that, then you will say, consider the x that's equal to bleh, and note that it does the thing. Yay, there it is. Okay? So that's usually how it's done. Not always true, because some proofs don't actually specify exactly what the thing is. So your subspace proofs has two of these. It has an if they're in the subspace, then this happens. The other thing that it has is just a bold-faced statement of this happens. In which case, you know, in which case your proof will just have random stuff and then you'll say therefore. You have no real choice. There's no place to start with that this happens. You just have to say that it happens. So when you watch people do proofs, when you watch your lecturer do proofs, and any time now or in a future course, watch closely the statement they're trying to prove and the structure of the proof that they're doing, and you will see this happening. You will see that certain statements tend to have certain structures to the proof. Not to say that proving is a game where you have to, you know, satisfy all of the conditions for how you do it. This is just more sociology than anything else. I noticed this about the way people talk about proofs. Okay, this is just how mathematicians behave. As I said, it's mathematicians 1A. Okay, so let's do an example. Prove that W, which is equal to x minus y is equal to 0, which is equal to z plus y, which is equal to 0, is a subspace. Okay. I mean, technically I'm supposed to say that these are supposed to be any real numbers. They're supposed to be like an in R3 here, but I forgot to put it in. Okay. Now I know that's a subspace because it's homogeneous linear equations. So I know already that it's a subspace and therefore it's possible to prove that it is a subspace because it is. Okay? Did you want to say something earlier? Or is it moment past?
I was actually completely off of this.
Okay, right. Sorry, I just suddenly remembered that you had your hand up. Okay, so if you want to prove that something's a subspace, you have to use the definition, and the definition of subspace has three pieces. And the first piece is that the zeroth piece is that the zero vector is in the subspace. Okay, so that's just a bold-faced statement. 0 is in W. So I'm not going to be able to start anywhere. I just have to finish, I have to write something here that finishes with therefore 0 is in W. That's what my proof is going to look like. So the only way to tell if something is in W is to use the rule which tells you if things are in W. That's the major thing to know about the way subspace proofs work, is that because you're talking about a set, and a set has a rule for being in it, and subspaces are all about things being in sets, you have to keep reusing this rule for being in the set over and over again, because that's what subspaces are about, being in the set. So how do I tell if something is in W? Well, it satisfies this rule. So let's see, 0 minus 0 is indeed 0 plus 0, which is 0. Therefore, the 0 vector is in W. Ta-da! It's usually as simple as that. So I probably gave myself a bit too much space to do that. Just when I write a 0 with a line under it, it's trying to write the number 0 in bold. That's what the underline means. So in your notes it's written in a bold font. An underline is trying to write in bold. And so that literally means, you know, I could if I really wanted to do this. You know, it's a 0 vector. Okay, rule number 0 is done. The next rule is scalar multiplication. So let's see. So I'm going to say suppose that U is in W and K is in R. Doesn't really matter what letters you use. Most people would use a little w if it was in big W. If it was in big W, but whatever. Some people use C instead of K. I like to use K because my C's look like brackets. Okay, so remember that the statement here in the original definition is if U is in W and K is any number in R, or it possibly says for any U in W, and so it normally starts with a suppose. Well, let's suppose we had one, and let's show that it's still in there afterwards. So at the end of our discussion, I'm going to put some working in here, and it's going to say, therefore, K times U is in W. That's my goal. I find it extremely useful to structure my proof writing like this, because it simultaneously tells me what I want to do and writes the proof for me. And also, if you can't finish it, you can at least say in this box at the end in your exam, I need to show this, and then at least you've shown that you know what you're supposed to do, even if you didn't finish, and it could make a difference between passing and failing or credit and distinction. Okay? You've shown knowledge, so they might give you a mark, even if you never get back to it later. Okay, so, well, this U being in W means that whatever the coordinates of U are, they have to satisfy this equation. And the only way I'm going to be able to talk about this is to say what the coordinates of U are. So let's say let U be equal to like ABC, or XYZ, or U1, U2, U3, whatever you want. Pick one that you feel comfortable with. Then A minus B is equal to B plus C, which is equal to 0. Okay, that I know to be true because U is in W. And that's the rule for being in W. Right? And so then I need to, well, let's see where we're going. I need K times U to be in W, which means what I'd need is I'd need that K, what is K times U? So K times U is KA, KB, KC. Okay, that's good. And the other reason not to use C is because then I can use ABC for my vector's coordinates without already having used C. So another reason to use K. So what I'd want is I'd want KA minus KB to be KB plus KC to be 0, just subbing this into the equation. Totally, I can just multiply everything by K, right? Done! Let's just do it forwards. Let U be ABC, so K times U is KA, KB, KC. Then A minus B is B plus C is 0 because it's in the subspace. So I should probably say since U is in W. And then multiplying by K, I've got K times A minus B, K times B minus C is K times 0. And then expanding that all out, I get this. And therefore KU is in the subspace because its coordinates satisfy the equation as well. Done. Awesome. How are we feeling? Okay. All right, last bit of the proof is about addition. So suppose U and V are both in W, and then I need to do some working and conclude that U and V, U plus V is in W. Okay. Right. Well, let me ask myself what things mean. What does it mean for them to be in W? Well, there was a rule for that. It's this. And so the only way I'm going to be able to use the rule is to write down some coordinates for those points. So let's see. Let u be equal to ABC and v be equal to DEF. Then u plus v is A plus D, B plus E, C plus F. Sweet. So everything has coordinates. Now, A minus B is B plus C, which is 0. And D minus E is E plus F, which is 0. I know them to be true because U and V are both in the subspace. Cool. And I need A plus D minus B plus E. Oh, I can just add the equations together, that'll do it. So A plus D minus B minus E is B plus E plus C plus F, which is 0 plus 0. So A plus D minus B plus E is B plus E plus C plus F, which is 0, and therefore it's in the subspace because it satisfies the equation. So W is a subspace. Right. That's how I would go about proving that things are subspaces. I made a lot of decisions when I did that, and that's one of the things that makes proofs difficult, because to do a proof you have to make lots of decisions. And deciding things is the most difficult part of doing anything. And it's also the most tiring part of doing anything. So decisions tend to tire people out, which is why these revision seminars are so hard for me, because I have to decide examples all the way along, and I get exhausted. So that's one of the things you need to do, is decide how to learn how to make the decisions. And one thing that helps me make the decisions is knowing where I am and where I want to be. And every time I'm not sure what to do, there are two things that I will attempt. One is to say, look at something that I've written on the page and say, what does that mean? So I looked at, I'd written U and V are in W, and I went, well, what does that mean? And I go, oh, well, that means they satisfy this equation. And so I went and made sure that I could write down that they satisfied the equation. And anytime the other thing I do, if I don't know what to do, is attempt to expand brackets or add things together or something like that. It's never a bad plan to simplify stuff. Right. Yes?
So what if it's not equal sign, it's like inequality instead?
What if it's an inequality? Then it's not a subspace. So to be a subspace, there have to be equations equal to 0 and not inequalities. I'm very happy with you saying what if. What if is my favourite kind of question. You should always ask yourself questions of what would happen if this was different. Yes?
Adding slack variables, that doesn't make it into a subspace.
So stepping back, adding slack variables, that doesn't make it into a subspace. No, because it's equal to a number that isn't 0. So when you do slack variables in an inequality convex set sort of situation, those equations are all equal to numbers that aren't 0, so it's not a subspace. But if they were all equal to 0, then it would be a subspace, and you might be able to use subspace reasoning for it. Subspaces are actually a kind of convex set. They're just extremely special. These are good questions. So I would say something else, that your proof will look a little different if your subspace is written differently. My subspace was used equations, and so my proof will have an equation sort of feel to it because I have to use equations to do it. If your subspace is written as a span, then your proof might feel a bit different. And I really feel like, for completeness' sake, I should do one. Prove that that is a subspace. So I'll do the same thing I did before. I need to write something and say, therefore, the 0 vector is in W. So before, my rule for being in W was having an equation, and this time my rule for being in W is being able to write the coordinates in a certain kind of way, which is a bit different. So showing that 0 is part of a subspace that is made by equations is actually a little bit easier than this one. So let's see, can I pick A's and B's so it comes out to 0, 0, 0? Yes, I can. I can pick A and B both being 0. So if A equals 0 and B equals 0, then A plus B is 0, 0, 0, and therefore 0 is in W. That double arrow there implies that. Okay. So suppose that U is in W and K is a real number, and then there'll be some working of some sort. And then I'll say, therefore, that K times U is in W. Okay, well, if U is in W, then it looks like that. And so I can say, therefore, U is equal to A plus B for some A and B in R. Because that's what it means to be in this subspace, then it must be able to be written in this way. So I didn't have to, before I had to make up coordinates of my own so that they could satisfy the equation, but this subspace tells me what the coordinates are already, so I can just use them. Let's figure out what K times U is. Okay. Now this last coordinate is supposed to be equal to that one plus that one, so I reckon if I expand that out, it'll work. Yep, done. I believe it. If it was in this subspace, then this third coordinate would be that coordinate plus that coordinate, which it is. Ta-da! Actually, you've just seen me convert that subspace into an equation subspace. I've just said that this subspace is actually Z equals X plus Y. Yay! All right. Well, if U and V are both in here, then it must be possible to write them in the way of the subspace. For A and B and C and D are in R. And then U plus V, well, I can just figure out what it is. Oh, that's good. It's A plus C, B plus D, A plus C plus B plus D, which is the right format to be in this subspace. And we're done. Technically, I shouldn't call it a subspace until I've finished proving it. I should call it a set up until that point. Because I don't know for sure it's a subspace. Well, I do, but I pretend I don't know for sure it's a subspace until I've finished proving it. So therefore, W is a subspace. So I find it easier to structure it as the 0, the scalar multiplication, and the addition in that order, because they get more and more complicated as they go. Yep. So I can imagine a lecturer giving a question that said, you know, ABC, decide if these are subspaces, and if they are, prove that they are. Don't think it's ever happened before, but I would put it in if I were the lecturer. And so you would have to look at it and based on how it looked, choose whether it should be a subspace, which you can do now, because you can look at it and say, oh, linear equations, totally subspace, I'll prove it. Or you'll say, oh, that's got a squared in it, probably not a subspace, so I'll try and think of something that breaks the rule. Yeah. I don't know if there's any other proofs in your course, but most of them about subspaces. There are others. If you do want advice about proving stuff, feel free to drop into the Maths Learning Centre and we can talk about it. And yeah, so yes.
You mentioned how most of the time you use definitions, but if we were to quote a theorem in a proof, how do we quote it? Like, we just remember the theorem number in the course notes, like how do we actually quote
So if you did want, so the question is, if you wanted to use a theorem in a proof, such as, the fundamental theorem of calculus,
it didn't have a name, but like
so if you want to use a theorem in a proof, really the only theorems you should be using are ones that have names.
okay. What about the really big one in linear algebra?
Then don't quote the theorem, just say it is. But so the big one at the end of linear algebra, which is about determinants and things being invertible. Yeah, so it's about a matrix having an inverse essentially. Yeah. So that theorem, if you were asked a proof that was related to that theorem, then almost always you'll be asked to prove a piece of that theorem. So you can't use it. And secondly, if you were asked to prove using that theorem, they probably would have used the word show and not prove. And show means, well, use any facts that you think are true, that you know are true, and then you can just say it. So usually if you had to say somewhere in your proof, oh, the columns are linearly independent, therefore it has an inverse, you just say it and you don't quote the theorem. It's such a big theorem that people just assume that everybody knows it's true. If it was important enough for you to name in a proof, it would have been given a name. That's my usual rule.